Guys, welcome back to TechDose, and in this video we will look at some of all the subset XOR totals, which is from Leetcode number 1863. We will be looking at two techniques. One will be involving recursion and backtracking, and another one will be involving bit manipulation with maths. The proof of this second technique will be shown at the end of the video, so stay tuned till the end. Let's now read the problem statement. In this case, the XOR total of an array is defined as the bitwise XOR of all its elements, or 0 if the array is empty. For example, the XOR total of an array 256 is 2 XOR 5 XOR 6, which is 1. Given the array nums, return the sum of all the XOR totals of every subset of nums. Note that the subset with the same element should be counted multiple times. An array A is a subset of an array B if A can be obtained from B by deleting some, possibly 0 elements of B. Now, if you look at an example, like let's say the second example, then in this case, in order to generate all possible subset of these three items, you have two options to select or not select the given item, right? So with three items, you can have total 2 to the power 3 number of subset. And if you enumerate all the subsets, then it has already been given that you will have an empty set first, and then you can have only 5, 1, 6, 5, 1, 5, 6, 1, 6, and 5, 1, 6. Now if you take the XOR of all these subsets, then the 5's XOR will be 5 because there is only a single item. 1 XOR will be 1, 6 XOR will be 6, 5 XOR 1 will be 5 is this and 1 is this one, right? So if you take a XOR, it will be 4. So 5 XOR 1 is 4. Similarly, 5 XOR 6 will be 3, 1 XOR 6 will be 7, 5, 1, 6, all of them XORed will be 2. Add all the XOR values of all the subset and then you get 28, and that is how this can be calculated, right? So this is the brute force approach by doing the enumeration of all the items. But if you look at the constraint, there are maximum 12 items. So if you write a 2 to the power n algorithm, because if you have two options for each item, then you will end up with 2 to the power n such combinations. Then this will boil down to 2 to the power of 12, which can be written as 4 times of 10 to the power of 3, where 2 to the power 10 is assumed to be 10 to the power of 3. This is way below your 10 to the power of 8, and definitely this is going to run well within 1 second, right? So even if you write the backtracking or the recursion algorithm, then this is going to pass. All the array elements are within the 32-bit integer. Actually, it is a very small number, 1 to 20, right? Now let's look at how to solve this by recursion. So simply, if I have an array having 3 items, let's say 4, 3, 5, I have already given the bit representation for all of them. Then I can generate all possible subsets. And in order to do that, I can make the recursion tree diagram simply. So I will start iterating from this first item, which is 4, and I will start with a XOR value of 0. I will keep a sum of all the XOR values of every subset, and it will be initialized to 0. Now I have an option to either not include this 4 into our subset or to include this 4. If I don't include this 4, my XOR value will remain to be 0 and I am at 3. If I select not to include this 3, then my XOR value remains to be 0 and I am at 5. If I decide not to include this 5, then my XOR value here will be 0, and so 0 will be added to the sum and it will still remain to be 0. Now I will come back to 5 and try to include this 5. So if you include this 5 XOR with 0 will be 5, so the XOR value here is 5. This is for subset which has only 5. So 5 will be added here and the sum value will become 5. Then you return back to 5, go back to 3. Now you try to include 3. If you try to include that, then 3 will be XORed with 0, and so the XOR value here will be 3. Now if you do not include this 5, then you reach to the end, which only has 3 as the XOR value. This is for the subset which has only 3, and so 3 will be added and the total sum will reach to 8. Now you come back and try to include this 5. Now if you try to include 5, then you already have 3 as the XOR value. 5 will be XORed with 3. So if you XOR 5 with 3, you see that this is unset in 3, so it will be 1, this will be 1, this will be 0. So this value is 6. So you will have a 6 here. So 6 will be added to this and it will become 14. And now you will come back. So this 6 is for when 3, 5 both are included, right? Now you will come back, go back to 3 and go back to 4. Now you will try to include this 4. If you try to do that, 4 will be XORed with 0 and the XOR value will be 4. If you try not to include this 3, XOR will be 4. If you try not to include this 5, then the XOR will be 4. This is for the subset only having 4, and so 4 will be added here and this will become 18. And now you go back to 5. Now you try to include this 5. If you do that, then 5 will be XORed with this 4, XOR this 5 with 4. Only 1 will be remaining, right? And this is for the subset which has 4 comma 5. So only 1 was remaining, 1 will be added and this becomes 19. Now you go back to 5, go back to 3, and now you try to include this 3. If you try to include 3, then 3 will be XORed against 4. Okay? And once you do that, it will become 7. Now if you try not to include 5, then you reach to 7, which is for the subset 4 comma 3. And so 7 will get added here, and this will lead to 26 value. Now you go back to 5 and try to include this 5. So 5 will be XORed against 7. You see, 5 will be XORed against 7. So the value will be 2 here, which is for 4 comma 3 comma 5. And so 2 will be added to it and the value will become 28. Right? And then you go back to 5, go back to 3, go back to 4, and you are done. So in this entire recursion approach, the sum value will be updated to 28, and that is our final result, right? So the total number of nodes in this tree will be 2 to the power of n, where the height of this tree is n. And since the height of the tree is n, due to the recursion call stack, your space complexity will be order of n, and the time complexity will be 2 to the power of n, because at every node we are just doing constant operation, which is taking the XOR. Okay, taking the XOR with the current item, that's it, and making the 2 recursion calls. So this is the simple brute force approach which is going to pass definitely, right? Now you have seen the recursion tree diagram. Now let's try to understand how to solve this with an optimal bit manipulation with the math approach. Okay, so I will do the problem deduction here. You already know that let's say the array is 4 3 5, then I can enumerate all possible subsets, and there will be 2 to the power 3 possible subsets for these 3 items, which I have already written. Now I have to calculate the XOR value of all the subset. For an empty set it will be 0, for 4 it will be 4, 3 5 it will be 3 5, for this 4 3 it will be 4 XORed with 3, which is 7, right? So accordingly I have calculated, and I have already given the bit representation using 4 bit. Okay, now the answer should be the sum of all the XOR values, which will be 28 in this case, which we have already seen, right? Now if you look at any number, like let's say I show you this number 0 1 1 0. In this case, this 1 is the first bit, because the bit will be counted from right to left. This 0 is the 0th bit, this 1 is the first bit, this is the second bit, right? So here for this XOR 6, since 6 has a value 0 1 1 0, so the first bit and the second bit are actually set. This is saying that the first bit is actually contributing to the final XOR sum value, and the second bit is also contributing to the final XOR sum value if you take the subset 3 comma 5. Okay, and that is how you got the 6, isn't it? So instead of adding all these values one by one, you can also say that in how many subsets this 0th bit is contributing, plus in how many subset the first bit is contributing, plus in how many subset the second bit is contributing, third bit is contributing, and so on till the maximum number of bit is contributing, right? So in this case, since the maximum number is just having 20, then you can say that it can be represented well within 5 bits. But I will assume that, let's say it is an integer number, so it is a 32-bit number, right? So I will be checking for all the bits from 0 to 31, that is 32 bits, and add each one's contribution. That will also lead us to the same XOR sum value. And how to do that? If you have not understood till now, let's look at how to solve this. Like the 0th bit is set in 4 subsets. You check it out. In 4 subsets, the 0th bit is set. Okay. So the contribution of the 0th bit will be equals to the number of subsets in which this 0th bit is set multiplied by what is the weight of this 0th bit, right? Because if you see what is this 3, this 3 is equals to 2 to the power of 1 plus 2 to the power of 0. Because the 0th and the first bit is set, and that is how this 3 has come, isn't it? So you can always represent all these numbers in this sum of powers of 2. Simply in sum of powers of 2 you can represent all of these numbers, and that is why taking the XOR sum is equivalent to saying each bit's contribution. Each bit's contribution, you just add it up, it will be the same as the XOR sum, right? It is always true. So we don't need a proof for this thing because this is a basic of bit manipulation. So if you say that 0th bit is set in the 4 subsets, then its contribution will be the number of subsets in which 0th bit is set multiplied by the weight of the 0th bit. Weight of the 0th bit is 2 to the power of 0, and if it is contributing in 4 sets, then it is contributing a total sum of 4, which is true in this case, right? It has 1 1 1 1. It is contributing 4 to this 28. To this 28, the 0th bit is contributing 4 sum. Now if I talk about in how many subsets the first bit is contributing, so you see the first bit is set in 1 2 3 4 subsets, right? So in 4 subsets the first bit is set and the weight of first bit is 2 to the power 1, which is 2. So 4 times 2 is 8. So the first bit is contributing a sum 8 to the total XOR sum 28, right? Which I have already written here. Similarly for the second bit, you see 1 2 3 4. In 4 subsets the second bit is set and the second bit's weightage will be 2 to the power of 2. It is contributing in 4 subsets, so the total sum it is contributing to this XOR sum, final XOR sum, is 16. And for the third bit, it is not set in any of the subsets. You check, it is not contributing in any of the subset. So its contribution will be 0 subsets multiplied by the weight 2 to the power of 3, which will be 0. If you add all this, then the total sum is coming to be 28, which is always the same even if you had not used bit manipulation, because all these numbers is just a sum of power of 2, right? I think this part is clear. Now for the main part, if you have done this enumeration, then you might figure out that a set bit will only contribute to half of the total subsets, exactly half of the total subset. But I haven't shown you the proof for why this statement is true. So just for the time being, let's assume that a set bit will contribute to half of the total subsets, which is if you have n items here, then if I know that the first bit is set, then it will be set in half of the total subsets that you can present. So the total subsets that you can have is 2 to the power of 3. Half of this is going to be 2 to the power 3 minus 1, which is 4 subsets, right? So I'm just assuming that a set bit will contribute to half of the total subset. I will prove it at the end why this is true. Okay. Therefore, once you know that, then the total contribution for the ith set bit will always be the number of subset contribution, which is always 2 to the power n minus 1 according to this given statement, multiplied by the weight of the ith bit, right? So this problem now boils down to knowing if the ith bit is set or not set. How to tell if the ith bit is set or not set? Well, in order to do that, you have to take the array and find the bitwise OR of all the elements. Because if you have seen at least one set bit, the final bit in the bitwise OR is going to be 1, right? And if all the bits for that position are 0, then only the bitwise OR will be having a 0 value, right? So taking the bitwise OR is very, very intuitive, because that will tell you which bits are actually contributing to the final XOR sum subsets, right? So you take the bitwise OR of all the elements, and then whichever bit positions have set bit, those all bits will be contributing to the final XOR sum. Okay, you can take another example here for 4 5 1. You see I have given the enumeration. So if you find the bitwise OR, it will be 0 1 0 1. So here the second bit and the 0th bit will be contributing to the final XOR sum, and the total contribution here will be in how many subsets this second bit will be contributing? Exactly 2 to the power 3 minus 1, because 3 is the total number. So the total subsets here will be 2 to the power 3, which is 8. So this set bit will be contributing to 4 subsets according to our previous statement, right? That we are assuming that a set bit will contribute to half of the total subsets. So this will be contributing to 4 subsets, right? And what is the weight? It is 2 to the power of 2. So 4 times 2 to the power 2 will be 16. And this is having a weight of 2 to the power 0, which is 1. And this will also contribute to 4 subsets. So 4 times of 1 will be 4. So total contribution will be 20, which is the XOR sum, right? So I think solving the problem is clear. So let's now see the proof of the subset count contribution. Now let an element X have the ith bit set and the array has n elements. Then let's say that the given array is X comma A2 to AN. So we have a total of n elements, and I'm assuming that the element X have ith bit set. So my goal here is to count what will be the total number of subsets in which the ith bit will be set. That's what I'm trying to find. Okay, what will be that total number of subset? So if I know that X has ith bit set, then from the rest of the items from A2 to AN, let's say that any of the subset that I can generate, I will be denoting it by S. So S is any subset which is formed from the elements of, from all the n-1 elements, which is from A2 to AN, right? So how many combination of such subsets can be formed? 2 to the power n-1 combination of subset, right? So S is a subset from the remaining n-1 elements, leaving out this X. Count of such subsets will be 2 to the power of n-1, right? Now let's assume any subset. Let's say that S is equals to A2, A4. I mean, it can be anything, but let's assume that it is A2, A4. And let's say that the XOR of this entire subset is equals to Y. So Y equals to XOR of a subset of S, right? XOR of the subset S. Now, two types of subsets can be formed to get the ith bit set. Now my final goal is to, whatever subset I make, the final output, that means the XOR value, should have ith bit set, and that is how the ith bit will be contributing, isn't it? Now if you look at the previous enumeration, when I can say that this second bit will be contributing, when I know that the subset which I have picked, if I XOR all the items, then the second bit should be set. If that is true, then only I can say that the second bit is contributing in this particular subset, isn't it? So that same logic is applied here, that two types of subsets can be formed to get the ith bit set. If you want to include X, let's say that I want to include X in such a way that X XORed with your Y should be having the ith bit set, Now I already know that X is having ith bit set. That is what I have assumed. Let an element X have ith bit set. If ith bit is set here, and if the final XOR value should have ith bit set, then what will be the value of Y? The value of Y should be 0 for the ith bit. It cannot be 1. It cannot be 1, right? So X XOR Y will be taken only when the Y is having the ith bit as 0. So this will give the ith set bit only if the ith bit is 0 in Y. And if you consider the cases where I will not include this X into our final subset, that is also possible, right? And that I will always do if the Y's ith bit is set. Because if Y's ith bit is set, you cannot include X. Otherwise the X's ith bit is set, Y's ith bit is set. So the XOR value will give you 0 for ith bit. So that will not contribute. Okay. So these are the only two cases which can happen. So it will never happen that a subset A2 comma A4 is taken, which will give you X XORed with A2 XOR with A4 equals to ith bit is set. And if you don't take X, then also the ith bit will be set. It is not going to happen, right? So what it will boil down to is, since all the subset of S will have the ith bit either 0 or 1, can you have any other number for the ith bit? No, right? You can only have 0 or 1. So if you have 0 value, then take the XOR with X. If you have a 1 value for that subset, then take it separately. Don't take it with X. So they will all contribute to the final subset. They will all contribute. That means all possible subsets that you can form with n-1 items will all contribute to make the ith bit set. You may have to double watch this explanation, right? Therefore, 2 to the power n-1 subsets contribute for X. I will show you an example here. If you take this 4, 3, 5, and if I want to first know like what are all the set bits which will be contributing, then take the OR with all the items, and that comes out to be 7. 7's representation is 0, 1, 1. Now if I consider this second bit here, okay, second bit, In how many subsets is second bit contributing? So let's assume that I know that the second bit is set in 4. Second bit is set in 4. So according to the previous representation, my x value becomes 4. Now S will be all possible subsets that you can form from the rest of the items, which is 3, 5. And what can be all possible subsets? That enumeration I have already given. This will be all possible values for S, right? Now if I want to find out the contribution, like in how many subsets will the second bit be set, because the second bit is set according to my OR value. The OR value is saying that the second bit will definitely be contributing to the final XOR sum. Now let's see this. This S is having the second bit as unset. So if you take this empty set and XOR it with X, then the ith bit will be set, because it is unset here and X is guaranteed to have ith bit set, which I already know. Okay, so this is one subset. Now let's say for this 3, the second bit is not set. So again for this 3, I will XOR it with X and get the ith bit set, which is the second bit set. Now for this 5, the second bit is set. So what I will do is I will not take it with X and I will say that the ith bit is set, which is completely fine. And if you take this 3, 5, I will see this second bit. Okay, this is set. So I will not take the XOR with X. I will just take the same subset and I will say that the second bit is set. So how many subsets are present in which the second bit is set? It will be exactly 2 to the power of n by 2, which you can say 2 to the power of n minus 1, right? So in this case, it will be 2 to the power of 3 minus 1, which will be 4. So exactly in 4 subsets, the second bit is set. And if you find out any set bit, even the first set bits, the 0th set bit, all of them will have 4 subset contribution. That will always be true. And that explanation is already given here, right? So you can just go through it once again. You will definitely understand. So this is the entire explanation for the proof. Therefore, the total contribution will be the subset count multiplied by the weight, because I know that this weight is 1, this weight is 2, this weight is 4. And you know that each of the set bit is having 4 contribution, which is 2 to the power of n minus 1. So multiply 4 with 1 plus 2 plus 4, and that will be your result. In this case, it will be equals to 28. So this 16 contribution is only for the second bit, okay? If you add the first bit and the 0th bit, total contribution will be 28. So I think the proof is clear. So let me now wrap up by showing you the dry run. So if you take the array 4, 3, 5, the step 1 is to calculate the bitwise OR of all the elements. The bitwise OR will tell you what all bits will be contributing. So if you get a 7 here, in this case you get a 7. This means 3 bits will be contributing. Now you have to just add the contribution for each of the set bit, and you already know that each of the contribution will be exactly 2 to the power n minus 1 subsets. So you can take 2 to the power n minus 1, multiply it with the sum of all the weights. So in this case 2 to the power 0 plus 2 to the power 1 plus 2 to the power 2, which will come out to be 28, right, for this particular example. Now this is just for this example, it is coming 0, 1, 2 powers. It does not mean that you can form it in the form of a series, because if this bit was 0, then this would have been removed. Okay, so you have to be careful about that. So the time complexity of this is order of n, and the space complexity is order of 1. You should always remember that whatever is the OR value here, this is actually the sum of all the weights. Sum of all the weights is equals to the OR value. Okay, let's now look at the code. If you are someone who is looking to prepare for top product based company within a limited time of just 3 months, then we have brought for you both the DSA and the system design live interview training program. The most important feature of this program is you get a filtered and condensed structured curriculum, in-depth discussion of all the topics, and my guarantee of your understanding, one-on-one guidance with me, and live weekend classes. To know more about the training, you can WhatsApp us on this given number. In this code, we are given the nums array, and I will be taking the number of items with the OR value initialized to 0. So I'll be finding the OR of all the items. This OR is actually the sum of all the weights of all the items, right? And if you multiply it by 2 to the power of n minus 1, this is the total number of subsets in which the contribution for each of the set bit is happening. And so this will be giving us the final XOR sum, right? So I think we are clear with this entire approach. If you still have any doubt, then feel free to comment below and I'll try to help you as soon as possible. Like and share our video and subscribe to our channel in order to watch more of this programming videos. See you guys in the next video. Thank you.